Attempt to probe.
And
Yes.
yes. So, whoop, you don't jump. HDMI is very sensitive. So yes, I'm Laetitia. I come from Sorbonne University, which is former UPMC, Paris 6, whatever. But I'm not in the math department, which we probably know. I'm in the geoscience department. And I've been using Petsc with Dave and Jed, and lately Patrick did also something in the code to develop a geodynamic code called pTatin3D. And what I'm going to show today, because I'm really not the math person, it's more like we had a problem, how we try to solve it using Petsc Library, me as I'm the problem person, and then they are the solving person. And then what it brings back into the Petsc Library in the end. So what I do, as I said, I'm a geologist, so normally that was my dream job before, sit on a rock in Greece, it was nice. But usually I don't use the hammer. This is just like from time to time they take me to the sun, but most of the time I'm in the lab running numerical experiments, so my rocks are different colors than the regular geologist. So why do we do a lot of modeling? Because you've seen a lot of geophysical or geological application this week. We do that because actually if we look at all the knowledge we have of the planet, so it's nice, a lot of color picture, but basically there are people who are like chemists doing some analysis, there are people measuring how the planet deforms with a GPS, people looking at wave propagation and doing actually model of that. People deforming rocks between two diamonds to see how rocks behave at very high pressure. So that's how we study Earth, or we use satellite data to see the gravity field. But with all of that, we have the geophysics that gives us information on today's structure, and it's very bad if you go to depth. We have a lot of information close to the surface, and it's not even data. It's actually, we have data, but the rest is model and interpretation, so we have modeling there. And if we take we can only collect rock at the surface. Remember, the biggest drilling hole on the planet is 10 kilometers, 11, and it was done during the Cold War, so we are not doing this stupid thing anymore. So basically, we only have the surface, and when you go at the surface of the Earth, there are a lot of very recent rock, but not a lot of very old rock, so the information also decreases. And all this white thing is like using thermodynamic modeling or geochemistry or like rock torturing at high pressure to give some constraint, but the rest is completely unconstrained, so it's completely open to modeling, and that's why it's going to be more and more simulation, I think, in the field of earth science. So my everyday life is to take basic PDE. Usually we can add more, but we have just conservation of mass, momentum, and energy. That's the strict minimum to solve a problem. And then we put some realistic behavior, like rheology. We try to set initial and boundary condition. And and then we go to see math people, so they do better than, let's say, MATLAB. We try to put it into a linear algebra problem we solve. And then my job is mostly to make the nice picture at the end. Well, I also pressed the button before, but I'm not developing this. So that's what we need. We need some numerical methods. Some people use finite difference of finite element. The two things exist in the field. Then we have problem with solver. That's why I'm here today. So we need robust linear and nonlinear solver because we have a lot of variation in the coefficient. And then the rest is actually to value these codes and do something. So that's the brain part, question, modeling, prediction, and going back to data. And the rest is the collaboration part, because nobody can do everything at the same time. So, as I said, I'm doing tectonics. So tectonics are the people who study the faults at the surface of the Earth, and they study the structure. It's just like when you build, you're doing this like building, but suddenly you want to build mountain. That's what tectonics is about. So it's really like some are close to the solid mechanics because we have like sometimes interface, but because we do on the long term, like when people are studying the building, if it crashes, they just know it's going to crash, so they make it stronger. But we want to know how it behaves after it's broken. So that makes our problem a little bit more difficult. And again, we have like all type of data that I'm not going to go, but same geochemistry, thermodynamic modeling to try to understand how we make a mountain or a rift or whatever, but anything that you find at the structure of the Earth, possibly in Greece by the sea. That's the most important part. So that's what I say. So the code we look for are this like long-term tectonic code. They can make, this is strain rate, they can make like shear bands, a lot of them, and they can deform. Like that's the structure you have in the end. It's complex, but it started with something flat. Actually, the world is 3D, so most of the time we need 3D. And this problem, they just lie at the border of what I call short-term tectonic problem, basically earthquake, where the geometry is not changing, so you can mesh the interface and just go with like the solid mechanics approach, which is like well done by engineer. And what people know very well is also a global convection model, which is just fluid dynamics with no free surface, nothing. It's just viscous, like it's Stokes flow, and it doesn't really need free surface. So this is like typical thing you see in the fluid dynamic engineering department. But in the middle, that's us. We need to have topography. So we need this free surface. We need to have like highly variable viscosity. We need to track interface between this type of rock and this type of rock because they don't have the same behavior. And this rock, they might fail and make this shear band, and we don't know where they are going to occur. So we need to compute where they will occur and then to accumulate large displacement on them. So that's why Jed says, I have tough problems. That's the cool thing. I have tough problems. So people are modeling that for many years, like with different methods. So Paravos Flamma is a FLAC-based version because at the time there was no memory in the computer, so people were running explicit everything. And then people started to use like more like a fluid dynamic approach with Sopal, Underworld, Duar. All of these are based on Stokes somehow. Slim3D was more like on the elastic side, but most of these codes are based on Stokes and are like finite element. Well, I would not call FLAC finite element based. And the second thing is to track things. All these codes use like a particular method to track where are the different element of the model going. So everybody is tracking particles in those codes. That's for the difficulties. So with all these codes, you might think that it's okay, we can solve problem, but actually, well, none of them really work. So it's not why. Well, the FLAC has all the problem of FLAC. Basically, there is no treatment of convergence, nothing. And then all the top list, they were using like elements that are not stable for incompressible flow, so they are not stable. So basically, either you need to use a direct solver, or you can try to use like a multigrid, but it's not going to converge because the element is not stable. You can stabilize the element. That's what you had in one of the version of Gale and Underworld, and then I think Phantom. I mean, some of them have the stabilized element, but these elements, they produce really, really bad divergence. I mean, the flow is not divergence-free anymore, so the AMR converge, but your solution is bad. So actually, at the moment, what you need to do is either you use high-order elements like Q2P1, like we have in pTatin that I'm showing today, or you use finite difference staggered grid, which is like much cheaper and works well, but doesn't really have a free surface because you can't deform in the mesh at all. So that's where we are at. So what is pTatin3D? So the idea of pTatin3D was just like first you have like some problem you want to solve, and then we will do the implementation. So it's not like, that's the way it started, because it started with nothing. Just me saying to Dave, doesn't work. I'm trying with this and it doesn't work. So that was science, that was the science part. So that's like the discussion on what we want to do. Like we don't want to use a cheap element because it's going to make it cheaper. Because in the end we know, because I already tried with Gale and all the things. I tried and it was not working. So that's why I'm complaining. So it's like, okay, if we have to take a good element, we take it, and then we try to make it faster. And then, yeah, what you want to achieve is like that people in 2D can get results on their laptop, and in 3D, like you can get good scalability and run big problem when you want to, because typical users are like an oil company who wants to have this simulation done, so they can give you as much CPU time as you want. You can have your, like you can have a very big computer if you are able to run a simulation on this computer, which is not the case of most of the code I was showing before, because some of them rely on OpenMP. So it takes 3 months for a simulation, which is not acceptable. And then, of course, when you want to do that, some of the problems are easy, some are very tough. So you want to be able to, not to have your solver, like we wanted to be able to change the robustness of the solver on runtime, so that we can adjust according to the problem anything you want to put in the solver, either the nonlinear or linear solver. So as I said before, the governing equation of the problem is, pTatin relies on Stokes flow. And then we sort of, at the same time, but not completely couple, the conservation of energy, so reduction diffusion of heat with some source term. And then you can have, like, you can make an evolution by advecting all these components and how they change with time. And everything is incompressible, so this incompressibility is the start of all the problem, because of course we have a new pivot in the system, but this is a standard, so I'm not going to go, like you all know better than me. So basically you do a short complement to get rid of it, and we use iterative method to get rid of the DVU zero pivot. That's the way. I'm sorry, I'm not a mathematician, so I just call that a zero pivot, not a whatever problem. So for spatial discretization, as I said also a little bit before, I guess I will repeat a lot of things because 45 minutes is long. We use particles, so we need to be able to resolve things, like to resolve interface between, let's say, a granite and a limestone, which are very different pieces of rock. And we need to track that with large deformation, so we put all this information about like the properties on the marker. And then also the evolution, like let's say, is this piece of rock, is it deformed or not? And so all this deformation, we will track the quantity of the marker to do all the evolution. So we need to be able to advect this marker correctly through the grid. So, and then all this information from the marker, they need to be then back projected on the ghost point to solve the equation, which make a lot of diffusivity arise, of course, but that's the way it works. And so what is really like the issue, as I said before, is that on the first 100 kilometers of the Earth, the temperature is, the heat is mainly like transport by conduction. Okay, so what happened is that in this first 100 kilometers, we're going to change the temperature from 0 degree or 12, let's say, or 11 this morning in England, to 1,300 degrees. So so basically you're almost at the temperature of melting. It's not melted, but you're almost melting. So, and at the first order, the viscosity of rocks, it varies a lot with temperature. It's just an exponential dependence on temperature. So even if you make your rheology very linear, what happens in your code is that you're going to have coefficient that varies by 10 to the 6. So you cannot do isoviscous in the lithosphere. You have 10 to the 6 order of magnitude in your viscosity just from the temperature dependence. And of course, all these things have to change place, and the structure is going to arrange. It's not horizontal. So, but that's what we have to deal. Like typically, that's the range, 10 to the 19 to 10 to the 25. For you, it's just going to be like, let's say, 10 to the 6 contrast. So we cannot go for isoviscous solver. You start to see the problem. And on top of that, that's just the dependence to temperature, but actually we also have like a dependence to stress, which is extremely nonlinear. Basically, because we want to make faults, and these faults is just like you get to a yield stress, and then it has to stay at that yield stress. So you have to enforce that the yield stress is not overpassed. So it makes a really nasty structure in your viscosity, which is one of the biggest issues, I guess, now. I will come back to that. But basically, we compute a yield criteria which depends on pressure. And it depends on dynamic pressure. So your problem is very strongly nonlinear. And this allows to make the fault and to have the flow when it's warm and to have it strong when it's cold, basically. So again, what we do is we put like all the coefficients that serve to compute viscosity and density on the marker, then we compute pressure and temperature on this marker to compute an effective viscosity on the marker, and then we back project it to the mesh to get an effective viscosity on the ghost point. And you can choose how you're going to project this coefficient. Either you make an average that is constant, or, I mean, you can choose all that from command line in the code, and actually, yes, it changed the results. Don't worry. Yeah. But that's the way you can choose, and then you can study from command line option how this might affect your numerical solution. And it does, like, it has to be clear. So as I said, we introduced a lot of non-linearity in the problem. So basically, that's an homogeneous layer. So this time there is nothing. It's not like a limestone and a granite. It's just like, let's say this is a piece of limestone, and I'm stretching it. But because of this like yielding component, the viscosity is going to drop again by a factor of 10 to the 6, just to make this shear zone. So the effective viscosity in your model without shear is just going to drop. And it's going to be a very thin layer with a lot of different orientations, so you cannot really capture it like the way you're doing. You have to deal with it. That's it. So what do we do with that? Well, we linearize the nonlinearity, and then we finite difference the Jacobian, and we iterate. And does it work? No. But sometimes it does. So then we update at every time step the nonlinearity on markers and try to get a new solution, and sometimes it converges, sometimes not. So if I want to make a simple thing on what we have, because pTatin strongly relies on Petsc because it was developed with Dave May, so and then Jet, so you can imagine everything is Petsc almost inside. So we have the nonlinear solver that calls the Stokes solve, and then we have the two blocks, and all of this you can change. Thanks to Petsc, we can change all the parameters for command line, because for every problem we have, you can put some robust option that will give you a solution. That's what I do with my students. But if you want to go faster, well, you need to go deeper in setting up the options. So for some problem, you can really get acceleration, but then it will completely break on another problem. So then you have different level of interacting with the code. But at least you have the freedom to interact, which is what Petsc gives to pTatin that is very precious. So again, prototype of geodynamic model. So that's what I draw when I go to the field. That's my problem. The length scale can vary a lot. So, and then you can also try to do a subduction zone and study like the little thing close to the topography, but you need to have the full flow field, of course. And what are these problems? Well, even this problem here with linear viscosity can become nonlinear because of the advection of the topography, for example. So that's what we know. So basically we have nonlinearity that arises from boundary condition. You want to put friction. From the rheology, that's what I showed you before, but even from the topography, you can get big numerical instability because we're just solving Stokes, so there is no time integration. So we need to resolve integration in time. So we see this type like this is a big instability. The topography is doing like this. We call that a drunken seaman. It's basically like you're not walking straight anymore. So how can you deal with that? Well, the fact that we use Petsc makes it very easy, even for me, a geologist, because everything is there. So basically, I can try different strategy, different solver, just by changing like which kind of operator I want. Like, do I try the true Jacobian, or do I want to finite difference it? Well, it's just one option. So we can really try for all these staff problems that are all very different. We have the possibility to adapt the solver. That's the takeaway message of this slide. And because I'm a geologist and I'm not a math person, I'm looking at time to solution, or the solution in general. And if possible, what I'm most interested in is the time to solution. So sometimes like, I got it or not. So you can change to adapt to things. So that's what I was showing before. So you can have this big instability. So one way we were trying to stabilize that was an idea of Dave. I don't know if it works, but well, I will show. Sometimes it works. But the thing is that at least if you make this nonlinear formulation for the problem, normally it's unconditionally stable because it's really bad during a simulation. Suddenly everything crashed because your time step was not stable. So if you add that, at least it's unconditionally stable. But is it fast? And how can I make it fast? So either you can drop the time step, and really when you want to make like 30 or 50 million years, you don't want to take time step of 20. Or you can try to use this stabilization. So then I was comparing both. And that's what happened. Here is the line of the, let's say, time to solution with a constant time step, and that's with the nonlinear update. And what you see is that, well, you're faster with the small time step, actually, because this has problem, and then your time to solution might decrease and be better, but you don't really gain a lot. The only thing you gain is not that your time to solution is not going to be better, but at least you know your code is not going to crash in the middle of a time-stepping simulation. So you gain on stability, but not on time step. But what was cool, really, again, because it's a Petsc thing, is that you can try all those things very easily. You don't need to change the code. You can sit on your computer and just try. And I find that cool. But then for plasticity, you can also try other things. So that's another thing. So I was telling you plasticity, and this fault, it doesn't work. So I don't know if you can see well, but what happened in general is that the plasticity on the first time step does not converge at all. So that's basically your nonlinear residual, and that's the time step. So you see on the first two time steps, you get the nonlinear residual that are going up. And the team in Australia was nice enough to actually publish it, which is perfect. You know, it was a nice enough reviewer to say, yeah, go for it, publish that, because everybody has the problem. So, and then after a while, because you have some finite strain, it will converge because you change the rheology inside your material. But the first two time steps, it's very difficult to make it converge. So basically, you start with an error, and then you time step on an error. It's a typical thing we do in earth science. So I was trying to find a way to avoid that on the first time step by changing the solver. And once again, it's not very difficult to set up that with Petsc, because you create new solver very easily. Even if you're a geologist, you can say, I'm going to have another type of salt. So one of the ideas was actually to start with some kind of isoviscous and increase the viscosity at each solve. And then when you do that, you build the viscosity contrast slowly, and actually you can converge from the first step and not start with a wrong solution at the first time step. So what? I guess I'm not going in the right direction. Okay. So that's one. That was one of the things. I don't know what happened with my slides. Sorry, maybe. And then there is also like the problem with the boundary condition that was solved the same way with this continuation strategy on first time step. Was to start with first to get, because when you want to put frictional boundary condition at the base of your model, you also have problem. Everything explodes. So most of the people don't use it. Well, they could be useful, but. So what we do again is we do not time step, we just try to make small change in the problem we are solving to get towards the solution using not the math, because I'm not a mathematician. What I'm using is just the physics of the problem, and I play with the physics to make it more and more complex at each solve. So here is like first a linear solve to get some kind of velocity field. Then you put the pressure in, and then when everything is correct, you don't let it explode. Like you want to stay close to the solution and add a little piece of physics at each iteration. I don't understand what happened. Something strange with my slide. Anyway, so yes, I don't understand, but I think it's good now. So, so that's what happened when you do this continuation first. For the plasticity, then you get something that is a good approximation of the solution, okay? And then you can, because you're close enough to the solution, you can use Newton and actually converge. Because if you're too far, Newton is not going to converge, but what we could show is that if you make this good approximation, then you can converge the solution even for this tough problem. And if I would put my graph like this, it would look better. Anyway, I have a very bad news. So now we are back to geology because everything is driven by problem. So even if you converge, and let's say you converge, but most of the time you do not very well converge, the solution of the problem we are using is not really like what we want. It makes turbines that are going like this. And I did not show you what a real fault look like, but really the real fault, they look more like the blue line than the red line that comes out of our code. So that's one thing, just to change the problem. And then there is a real reason, because what we are doing at the moment is this thing. So here you see like the plastic strain, so cumulated plastic strain for 50 time step in your code. And what I'm changing is the resolution. You see a very nice strain to divergence with resolution. that is coming straight from the physics we are using. And of course, with that, it's going to be very difficult to use AMR or any kind of mesh that is non-conforming or different resolution, because all that depends really strongly on mesh resolution. There are some ways from engineering to fix it, but for the moment, it's not used in the... I think that's the next step, is to make sure that we manage to get to something that looks like the correct physics and converge in terms of nonlinearity. So that's for like all the nonlinear parts of my talk. I would say like that's where we are. I'm not sure you guys can help us with that, because I think we have to go back to the physics, to the geoscience, to the mechanics department. But we need to change the physics, because I think we can work on solver as much as we want. You can work hard looking at residual as much as you want. It's just not solvable with this physics that we are using. That's it. So, how much time do I have left? Okay, 15 minutes. Good. So the next step that we have, so everything I showed for now was 2D, so we want to run on supercomputers. So big problem in earth science, a lot of simulation has been done in 2D with a good or bad solution. But actually a lot of the problem on the planet are actually 3D, because things, even if the drawing, you see, actually we see all the problem of the geologists. You see the cartoon of the geologists are always cylindrical. If you look at the real Earth, it's not cylindrical really at all. But when geologists draw cartoon, all the ideas of geologists to interpret the world are based on numerical model, although they don't want to admit it. And they see the world in a cylindrical point of view. So we need to change that, because otherwise there are questions in earth science that will never be answered, simply because you cannot explain everything with a cylindrical model. So what we want to do is to do 3D geodynamic model of rifting, or subduction or whatever, but rifting is actually the simplest one. So what is it? For example, it's like, oh, I have two branches of rift coming here, and I want to see how they merge. So here you're going to see a movie of the strain rate, so how it deforms with time, with different cross-section through the block. So you see it propagates, and then it's going to merge, and it's going to make a nice non-cylindrical structure. And it's a GIF, so it's going to repeat, repeat, repeat. So that's what we want to study, because actually what happened in that part is not described in any textbook, because when people don't have concept, they cannot see. They cannot look at the data without the concept. They think they look at the data, but they look at the data with 2D glasses. So we need to create that, and that's why we need geodynamic code, to create new 3D concepts. So if I see, like, from my PhD time, in my first MATLAB solver, 10 cube, I wrote it my own. It was Q2 on MATLAB back in 2004. So that's what the size of problem we could do, like when I was a PhD student in 2004. Then I was using Gale Underworld, like another code which had the problem with the stabilized element, and just with that, because it was stabilized element, it dropped seriously, and we could really do, like, back in 2010, 12, 13, 11 I put here. Suddenly it dropped, and I could make, like, much bigger problem and start to see, like, 3D problem at crystal scale. And then, well, starting to work with Dave and making the thing better, well, and using an algebraic multigrid on a real stable element, now we can make problems that are at the scale that is the scale I was interested in the beginning. But that was my nuclear plant, and that's what we can do, so I'm happy. So that's where we are today. And so I feel a bit stupid explaining multigrid to you guys. So basically, what do we do when we want to do multigrid? We have a fine mesh, and then we coarsen it. We make some restriction, compute error, and we make this V-cycle. And I'm not going to explain because I'm not a mathematician, but that's what I understand. And on each of this level of the multigrid, you can choose and put a best solver according to what you need. Okay? So when we use the multigrid, like the way it was put in pTatin, what you see here is the viscosity contrast for a simple problem, which is a falling sphere with a free surface, which is very important because the most difficult part of the problem is to have the free surface. So what you see is that you can go, if it's an isoviscous problem, done it in 5 iterations, but we can go up to 10 to the 8 in viscosity contrast for the simple problem. It's going to take longer, but it's converging, so it's cool. If you want to make a harder problem with a lot of balls, because one ball is not realistic enough, well, if you can go up to 10 to the 6, which is the range I'm interested in, but it's true that at 10 to the 8, it's not converging anymore. But 10 to the 6 is really what you need to do a geodynamic problem. And I'm sure by torturing the solver, maybe we could converge with 10 to the 8, but I'm not sure it's needed. So how do you get there? But again, by adapting all the time like solution and testing different options, which is making it easier because we use Petsc. So that's like the scaling that you can monitor and that everybody in this room can monitor in general, with scaling from 64 to 4000 CPU. And well, the results are not too bad, I think. From what I say, it's not 2, but it's optimal. And I go there because I'm late. So then what we can do is to try different strategy for the different level of the multigrid. So we can use matrix reassemble or Galerkin and play with the strategy to see which one works the best. Of course, you're faster when you use assemble on the fine mesh, but your memory explodes. And if you look at that, if you use the matrix tree, okay, it's not as fast, but the numbers are not bad, and the memory, like you find the right balance. So there's a balance also between your hardware, what you want to do, and the size of the problem. But the cool thing is you can adapt and change all that from command line. And then there was another problem that arises, that actually what we find as a strategy is that the smaller is your coarse mesh, the better it is. The only problem is that you want to deal with 8000 CPU, because that's the size you want to have your result in one day or so. And then at one point you have a problem with actually you cannot make a small mesh like this. So that's why Dave started to develop this repart. So in the model that I was showing you, there was this like repartition so that we can remodel how you place your grid on the different 8000 processor. And that was all the goal of the talk, is to say that, so this was there because I could not solve my problem. And now you can all get access to it, actually, because it's called, I'm going to go fast, because it's now inside Petsc. So basically, first thing was me complaining to Dave and Jet, like, well, it doesn't work, it's too slow. And then this too slow is like, first they work, so we did a piece of code on our side that was like working, but now everybody can access it because actually it went back to the community. So that's why it's kind of cool, I think, also. Another thing that was developed really for pTatin was because I showed you already we use material point method, so we need to advect things all around the plate. We need to advect a lot of markers in 3D, so we don't care about that. It was just to say, remember that. So you know this problem, just to advect points of marker along the grid. It's very difficult, it's tedious, and actually most of the code in geodynamics, that was their bottleneck. It was a big bottleneck in the code in geodynamics, because we all want marker, and suddenly in 3D it was, where is the marker, how do I deal with that? So Dave did a lot of work for that in pTatin, and now you can all have access to it in Petsc, because you can just use swarm to have your swarm of markers that you can advect. And if you want to relate your swarm, so that's the API, it works like you just have it, you have example in Petsc. And then if you want to put your swarm with some DM, you have full support for different DM, because of course Dave was doing it with maths without saying to Barry, if I understand the thing. But nice in Petsc, so everybody can use those things. And again, it was just because it was driven by a real issue in earth science. We needed this point to be advected fast for our 3D models. So, question like, did we really solve something with the code? Because that's what I do. So yeah, I would say it's kind of worth the effort. So just to make a long story short, when we look at this continental rifting, I show you some models that are like this, with one ocean that is stopping the other, and you can make this shape like this that we see everywhere on the planet. They are called V-shaped propagator. And most of the people, they want to make V-shaped propagator by saying you have to rotate. The only problem is that we know how plate rotates. And we know that the pole of rotation is not there. Yes. So it's just like none of the models that exist could explain the data. So we needed an extra model to explain why a rift that is propagating this way, an ocean that wants to open, propagate this way, how can it stop? And so we did some model like this. And then what you see is that if you do it with cylindrical boundary condition and you make this rift, this is the crust, this is the temperature in the mantle. So basically you see, and now we see like the beginning to have like the accumulation of plastic strain. So basically it's the faults. And the faults, they propagate very fast and they will cross the model like super fast. You don't stop them, they go much faster than the velocity you put on the boundary condition. Okay, and then I'm going to open an ocean. So now that's the moment. When you open the ocean is when the mantle comes to the surface. So when you see the temperature at the surface, puff, here you have a mid-oceanic ridge. And it's very linear. It doesn't make like a V, okay, although it was propagating. Now, if you just put a little bit of compression, so basically when you really use 3D simulation, like 3D boundary condition, let's go faster. Don't worry, it's the end of the talk. What you see is that it does not, okay, that's the interesting part. It does not propagate as fast. You make this V-shaped thing. And now you see your ocean. It's the same time of time scale, but it's opening, but the speed of propagation of the tip here does not have the same behavior when you change the boundary condition. That's cool when you think in terms of PDE, that if you change the boundary condition, you change the solution. That's bad, not bad. But what is really interesting is it's really drastic. Like if I put free slip or a little bit of extension, I get linear velocity. And as soon as you put a little bit of compression on the top, you really change completely the behavior of your system and you get something that is completely styling. And is it useful? Well, if you take the same model and do a little bit more, don't worry, it's almost last slide. What you see is that you get the rift here with the ridge and the fault, blah, blah, blah. And this is the South China Sea, a place that a lot of people like at the moment with a lot of plastic deformation at the front, a propagator that was going like this and then turn and it got stuck here for 12 million years. Nobody can really explain. Well, basically we can produce it, but it's only in 3D. This result would not have occurred out of a 2D cylindrical model, so we would never get any insight from 2D, because you cannot explain this structure in 2D at all. So to conclude, today, thanks to all this work, it's never been easier to solve big, large Stokes law problem with variable coefficient, 10 to the 6, 10 to the 8. Really, it's never been easier. We made really nice problem with that. But now we have a bottleneck with the nonlinear solver, but I really think it comes from our side. We need to find a better way so that we get less nonlinear iteration with converged solution so that we improve the quality of our work in geodynamics. And the good takeaway message was just that actually it's fun because this paper is like accepted in Nature Geoscience, and it's the same simulation that was presented in SC. So basically the same model you can publish even twice because for different reasons. One that's solving some earth science problem, and one because you have a good solve time. And so let's say that we have a nice convergence, as you guys talk about, and the code is now released in Bitbucket, so everybody can have a look at it. Thank you.
Yeah, thank you very much. Okay, questions?
Yeah, no, don't worry.
People be intimidated into silence.
No, it's the normal thing.
Where's Jed? Normally you hear, Jed's in the US.
Yes.
Can you comment on the different smoothing you had for the high properties, the material properties? You said that varying them you got different results.
Yes.
And
I removed that slide. So basically, if you, depending how you project from particles to grid, of course, I mean, if you assume it's constant or it doesn't really converge. I tried many things. The real issue I see with that it changes, well, okay, anyway, this rheology has a problem. The real issue is that nobody in the earth science community actually writes in the paper how they do it. So But so I can comment, yes, when you change, because the rheology is wrong. I don't think there is any way we can fix that except by using some more advanced rheology. Probably one path to the solution is to add elasticity back, because that will give some scale in the viscosity drop. And then maybe we can resolve it, and if we can resolve something, and if the problem has a unique solution, we might find it. When we take something with no unique solution and no, let's say, scale of strain to get the thing to happen, well, you can iterate. It's never going to work.
Quick follow-up on that. Was any of that DM swarm infrastructure or functionality a part of changing that smoothing operation, or was that?
No. Yes.
Right.
Can you speak up, please?
Yeah, Dave.
Sorry, the PDN swarm implementation supports the altitude projection using the EDA. It's like a default. It's making them always one. Yeah.
Do you want to try? It's easy.
Any other question? I have one question if I can.
Yes?
And so for the nonlinearities, like say the fact is sometimes you don't know the terms, could you use, now that you've got a fantastic fast model, could you look at using adjoint state methods to maybe invert for the unknown rheologies?
There are people doing that, actually. I mean, not really that. I mean, I could not, if you want to try.
And you have the code.
Yeah, I have the code, but I don't really, it's not like I can, I mean, it
That's
could
next
be.
year's Petsc talk.
No, yeah, that would, no, not next year, I don't think so. No, but I mean, it could be something, because but really I would prefer to just change the rheology, but we can try to fix it. But I'm not sure it's worth fixing that implementation, because really the physics is not so good. But that would be a way, because the problem is, yes, you switch from solving your regular PD to an optimization problem, so using adjoint would help, because that's why it doesn't work, because really you switch, it's not the same problem you're solving when these things turn on, and we don't have the right tool.
Okay, well,
sorry about that.
thank you again. So, next up we have
Sorry.
Justin Chang.